Thank you all for coming to see Alan Hastings today. It was instantaneous that I thought of Alan when Alex proposed that there should be a distinguished alumni lecture series. Alan and I were nestmates. We both did our PhDs here with Simon Levin. My first year here was Alan's last. He got his PhD in 1977. Went to Washington State University for 2 years. Okay, very good. And then to Davis, where he has been ever since. He's now a distinguished professor in the Department of Environmental Sciences, Policy, and Management. And
that's the Berkeley one.
What? Oh, you're at
Environmental Science and Policy.
Environmental Science and Policy. Okay, let's see if I get the rest right.
Yes.
He is distinguished he really has had a distinguished career. He got the MacArthur Award from the Ecological Society of America, which is the highest honor that the society gives to mid-career ecologists. He was just elected to the National Academy of Sciences this year. He's had many students and postdocs who've gone on to successful, even prominent careers, and he has a frightening track record of moving into new areas in theoretical ecology time and again, and just making basic, important contributions that change how people think. And it is therefore a real pleasure to have him here today to kick off this series, and we have something for Alex.
So I wanted to add a couple of tidbits. I recently learned that he also had his undergraduate degree from Cornell, and that there are two more PhDs in the family from Cornell University. We are really appreciative of his coming here. He had to battle bad weather, flight cancellations, and such like. We would like to hope that he will have a better luck on his way back, but just in case, we want him to be prepared. So here are a few memorabilia from Cam scarf, a couple of Cam t-shirts in case he gets stranded at the airport. Well, it had to be an authentic coming to Ithaca experience, and after all, Homer wrote a book about it. And since you are the big cheese of the day, here's the big red cheese.
Now you can't say, cheese, you probably can say.
Cheese you can.
Yes, it's liquid.
Yeah.
Thank you very much. I was going to let Steve just talk for an hour and just sort of sit there, but the scarf is interesting. Earlier, well, I'm going to say because it was their winter, but basically I was in Dunedin, where somebody pointed out that people from Auckland who went to Dunedin who couldn't stand the cold and would be referred to as scarfies because they had to bring out their scarf even when it was warm. I've been in California too long. I've gotten way too soft. I will try and name the collaborators as I go along, but I may forget. And I'm going to go through, basically move from some environmental problems to some mathematics, but I'll keep the mathematics, try and keep it sort of simple so people can follow. So environmental problems are growing. In this case, it really is growing. That's kudzu, of course. So invasive species are one of the ones that I will return to. Zebra mussels are a huge problem. This is Caulerpa. This is an interesting one because people didn't know it was a problem at first when it was found in the Mediterranean outside an aquarium near Monaco. They then discovered it was a problem, so then when it was found near San Diego, they went after it with everything they had. Another sort of environmental problem that you may be aware of is overfishing or overexploitation of almost any renewable resource. And then, of course, the big problem, as is being discussed this week, the global change, in this case, the increase in carbon dioxide and its effects not only on temperature, but one of the big ones that I'll sort of mention that's sort of interesting to think about is the fact that it causes ocean acidification. And there'll be a quiz on the chemistry at the end. So what might we want to do? We might want to try and prevent undesirable changes. You might want to, once things have occurred, you might want to try and reverse them. And there are things that either you you really can't stop or don't have the will to stop, and so you have to adapt. So there are all three of those things. For people standing too, there are at least a couple of chairs up front. And one of the things is, though, understanding ecological dynamics may be much easier than prediction. And this is something one has to think about. But of course, decisions are based only on prediction. And one of the aspects is that we need to predict in a changing world. So you can't do what some people would like to say you should do, which is to go back and see what happened before the last time this happened. But there is no last time because the world is changing, at least in terms of that. And of course, that's why we're all here. The answer that mathematics can do a lot to help us. And what I want to do is go through this. And basically, among other things, you want to understand the limits to prediction. And for example, I have no idea what this means. I don't think anybody really knows, but you look at your weather forecast and it says there's a 30% chance of rain. There's some uncertainties attached to it. Who knows what that really means? But anyway, there's there. We can't stop with, say, understanding just the scientific or the ecological scientific aspects. We might want to think about economics. If there were no economic costs, presumably, we would all of a sudden do everything we needed to do to stop emitting carbon into the atmosphere. And even if we could figure out the economic cost that was economically viable, you still got to get people to change what they do. So the other aspects of human behavior is something I've started to think about a bit in context with some groups, but haven't done enough on. So after all these grand challenges, I'm going to look at some very small and specific issues today to try and get a handle on the sorts of things. And first I want to sort of go back and look at some older material, first some very older material, not my own, that gives an idea of kind of some of the issues and some of the sort of mathematical challenges, and also point out some things that people may not be aware of. So these two gentlemen, Locke is on the left, Voltaire is on the right. Sort of, it's interesting to realize that Locke basically for almost his entire career was not an academic institution, but worked for something like a life insurance company. And Voltaire, in addition to his career as a mathematical physicist and other things, was a member of the Italian Parliament. So this is a picture, and this presumably, although it's not written here, but I'm pretty sure that Locke knew what he was doing, is a graph of predator numbers against prey numbers, and must be a log-log scale. And this is a graph of what happens with the classic models that I assume many of you, if not all of you, are familiar with, where you don't have any density dependence, where the per capita rates of change of predator and prey are linear. And everybody says, okay, this is foolish, etc. But Locke really did know what he was doing, in the sense that if you turn the page, and it's actually you don't have to turn the page, at least it's right on the next page, is that he said, this is a way to understand what's going on at short time scales. You can understand a lot about this because you can actually compute these level curves which describe the trajectories analytically quite easily. And that if you then add on density dependence, you're going to get the solid line. But understanding the dashed line really tells you a lot about what's going on. And when thinking about the kinds of time scales that show up in ecological systems, that's an important issue. One can do lots of other things beyond the sort of simple, and something that becomes very important is adding various structure. One thing, and I'll return to this example in a minute, this is a Dungeness crab. Don't eat it this year, supposedly. There's some algae that's contaminating things and making it potentially rather bad to eat in terms of making very sick. We created a fairly detailed model where we had eggs, females and males of various ages. We had cannibalism on the eggs. And the one observation is this harvest term, where the harvest was getting essentially every male of harvestable age. And that gets complicated. And the females are infertile or dead because the males have to be bigger. The males that are bigger than that, if they're not harvested, they are subject to a castrating parasite. And we'll stop there. On the right is structured by space. One can also structure by adding in more species. But I want to return to that model which I just gave you the structure of without the details. The details are probably less important. We fit this model. This was work with Kevin Higgins and Lou Botsford and a couple of others a long time ago. We fit this model to time series of harvests, of landings. And these, as you see, are log scales. And so the order of, essentially the harvest would vary by almost an order of magnitude. So huge oscillations. The data we had was at that point was 50 years of data. We then had a very good fit to that time series. We then ran the model for 1,000 years to get a feeling for what would happen. All the growth statistics matched. But what's really interesting is this is a stochastic model that includes both stochasticity. And if instead we ran the deterministic version of the model, the only thing that would happen, rather than produce these kinds of dynamics, would be it would go to a stable equilibrium point. So one way to think about the dynamics either would be that stochasticity is absolutely essential, or to think about that the variability, the environmental variability, is essentially causing the system to always be in a perpetual transient, trying to return, and it shows up as these quite dramatic oscillations which appear to have some regularity. We can go through there more. Another topic which I'll at least touch on, that's of quite a bit of current interest, is this concept of tipping points of multiple outcomes. On the left here, we have a picture of an oligotrophic lake, one that is in a desired state, where it's clear, etc. On the right, we have something that's full of sort of scuzzy algae. BB Lake, I guess, at some points looks like that. Certainly the non-flowing water body on the Davis campus always looks like that. And that are two outcomes. And there's been a lot of work by Martin Skeffer and colleagues which have tried to look at this in terms of a transition. So what I've drawn up there, or copied actually from a paper by Skeffer et al., is a picture of a potential under two changes. You change the parameter, and for some reason they use mirror images. And when you change the parameter, you get to a case where if you perturb, it's going to recover more slowly, it's going to have a skew, it's going to have a higher variance, and a large enough perturbation would push things out of the basin of attraction. Another way to view this would be to think about it, instead of looking at the potential, to look at a bifurcation diagram, so plotting the system state against some external environmental condition, and we think about environmental change could be moving the system this way. If it passes the saddle node bifurcation, the solid line is stable, dashed line is unstable. It could reach a state where it would go down to a less desirable state. This is more desirable. If you have a large enough disturbance over here, it would go to a less desirable state, so it would switch perhaps from the more desirable to the less desirable state. People have posited, and this is from a paper by Tony Barnowski and sort of 20 others of us, or some number, that would saying that perhaps the same sort of thing might be happening at a global scale, and here thinking much more about just effects on terrestrial ecosystems, effects of increasing human population, than necessarily just the effects of carbon. And this is just a schematic, no actual data. What you would really like is a sign like this. This is actually near Santa Cruz, that would tell you that you're about to run into something. But the question is, do we have something like that? And what you really would like is, if you want to do management, it requires more than knowing that danger lurks. Because, for example, one might say that the problem is overfishing. And if you say, okay, well, we're in danger, we should stop fishing, that in itself has a huge economic cost. And so you have to be careful. You cannot just simply say that things are dangerous. And so you would like to know about how you would do this. And one thing which I'll return to a little bit, which is sort of how I got to thinking about this, which was coming from a particular system, that a mechanistic approach, an approach where you actually model a particular system rather than this sort of general approach that I sketched out for you could be useful. But even the general approach, you should sort of create a somewhat more mechanistic model, and you might want to get out of that the limits to predictions. So, in some work with Carl Bettiger, a former grad student who just started on the faculty at that other institution down the road in that department, ESPOM, that Steve tried to mention, we looked at this problem and tried to do it in a little bit more mechanistic fashion. So if you look at this, what we said was we're going to use a likelihood approach to fit a quadratic model because in some sense the unfolding of this bifurcation is a quadratic model. We write down two cases, one where there's no change in conditions and the other where there's a change in conditions. And again, since we're going to have the simplest case, we're going to either assume that the parameter is changing in a linear fashion or not changing at all. So either we're moving at a constant rate along this axis or we're steady at some point along this axis. And again, there's no sort of justification except that this is the simplest model that would capture this kind of dynamic. Once we do that, we compare fits, and so the idea is that we use a likelihood approach and use the model likelihood as an indicator. And in this sense, better we claim, or will claim, than ideas that were based essentially on just looking at some measure without justification in some sense of a time series. And one of the real challenges here is that you can't do what you would like to do. I showed the picture of the Earth. Clearly we only have one Earth, a single realization. But most of the time you want to apply these ideas, it's not that you have multiple realizations, not that you have multiple systems, and you're following one that's a reference and one that's perhaps may be changing or may not. You have a single system. You're collecting time series data, which clearly has some correlation in time. So we start with the obvious description. Here's our parameter. We either assume that RT is constant or changing linearly with respect to time. You assume that there's a fixed point, which is obvious. It's kind of straightforward. You write this as stochastic differential equation by writing it this way, where the scaling the noise term, the sigma term, by the square root of phi suggests that we're in the back of our minds thinking of demographic stochasticity rather than some other form of stochasticity. As I suggested, we do two things. We either assume that m is non-zero, or we assume that m is zero. So we assume that things are getting either staying the same or potentially getting worse. And so in the second, I write it down as though there is no m term. And then we look at the compute the likelihoods. I will not do that in public. Perhaps we'll even do that in private. So this is the likelihood of the parameters given the model, which is the right way to do things. And we look at a test statistic, which is the difference in the likelihood of observing the data under the two maximum likelihood estimated models. And I could go through, but rather than have you read that, it just says that we can do this by essentially doing a simulation, which then gives us distributions which allow us to estimate these likelihoods. There's a way then which is becoming used more that we used here, which is a very useful way of portraying things, is that, again, as I said, we don't want to say, okay, the right answer, especially for management, is not the scientific one, for example, that you might use. Is there some, can we say with some confidence that the system is going to tip, or some confidence is not? It's actually much more useful to say we estimate the probability that it's going to tip is something. We can assign an economic value to saying it's going to tip when it's not, and the action we take, and fill in all the cells the way you would, and then you can choose an action which in some sense gives you the highest economic value, and you can do this sort of issue in some other way. And so for this, a way to display things and how much information we're getting out is receiver operator curves, which or characteristics. Turns out actually that the Wikipedia article on this is surprisingly good. Not all Wikipedia articles are, so it's not too bad. And so the idea would be that we've generated a distribution of what the statistic that we're looking at would be either under, say, the idea of tipping or the idea of no tipping, and you're given a value, and what you want to do is ask yourself, which distribution does it come from? And so for any particular value of the statistic, I can plot this value and this value, and this will tell me the probability that there's a true positive and versus the probability that it's potentially not. And what we can do is we can go through that for every value of the statistic, and what we get is we get the a receiver operator curve, which then, as I tells you in some sense, for any particular, it sort of illustrates in a very convenient fashion how much information we're getting out. If this in fact sat on the 45-degree line, it would be telling you that you're getting no information out of your test statistics, because then, in some sense, the distributions would be lying right on top of each other. And what we did is went through and showed at least that the procedure that we have developed is a good way, probably the best way to look at this kind of question. And this is a way to at least make some progress and make an informed decision, or at least provide the information for making an informed decision. And I'm going to sort of, in a minute, switch to a couple of specific cases and just sort of point out that together with tying to social science, that there has been tremendous progress made in developing models, in theory with enough details, and in interfacing with the social sciences to make predictions based on this very recent, a lot of it based on this very recent contribution from 1763. Some of you can probably read, it's in the third line there, that would be the name that you would attach to it. But lots of challenges remain. Thinking about appropriate time scales. We've got good mathematical tools, good quotes probably, for handling small noise, yet ecological systems are probably subjected to large noise. If you've been here for more than one winter, you probably recognize that other than the fact that the sun never shines, say the other aspects of it may vary quite a bit from year to year, the amount of snow, the temperature, etc. Large noise is really what affects things. Making the best use of predictions, integrating not just with economics, but with other social sciences. People do not always behave in an economically rational fashion. There are limits to complexities of what we can analyze, and I'm going to go through, and I don't know how much time I'll have to go through these in detail, but go through two examples that sort of led me to these sort of more general aspects. One is in the management of invasive species, and I'll concentrate actually on a particular invasive species. So this is an aerial photograph of a portion of Willapa Bay. And Willapa Bay is just north of the mouth of the Columbia River. As you might guess, that the Columbia River has among the highest silt loading of any river in the country, because as emphasized by that thing that happened, what would be the spring of 1980, luckily a year after we got out of Pullman, Washington, that all of eastern Washington and that part is covered with volcanic soil, which very much washes in. This then is the bay that's enclosed by the silt that comes north out of the mouth of and if you know your fluid dynamics, etc., that's the way it should be going. So it's closed off. It's a very shallow bay, and what you're seeing here in this square, you see what looks like, right? Well, it almost looks like what? Bacteria on a petri dish. It's not. It's Spartina alterniflora, which is an invasive species. The natural vegetation here is nothing, literally nothing, a bare habitat. And it's actually very important for two reasons. One, there's not much on the west coast for shorebirds to feed on. This was very important for that. And the other, there's an introduced oyster. There's an oyster industry in this bay. that would have been destroyed had this done. And this is what looked like 2 years later, where the red is the same area. So advance. And so looking at this 3 years later, 3 years later, look at the advance of the, and so as I said, the natural veg state is bare mudflat. 3 years later, bare mudflat has been reduced, Spartina, and this is altered flora, and there's just about the same amount of native plants. I'm going to now give you another view of a sort of similar problem, the one that I'll return to a little bit later on. You may or may not recognize that that is the skyline of San Francisco Bay. This is San Francisco Bay. This is the nice mellow California, native California species, Spartina foliosa, and this is a hybrid between the nasty invasive Spartina alterniflora and foliosa, or else pure alterniflora. It's probably a hybrid. And here, again, this is the Spartina not only has an effect on crowding out the native, but it grows both higher and lower. It clogs storm channel drainages and changes views, so it has a negative economic effect. And so what we did is we started off first with a spatially explicit stochastic simulation. And I'll just throw quickly in that something called an Lee effect, the fact that at very low population densities, the Spartina actually produces less. It turns out to be so important to include. And then what we did is we compared this to an analytic model to justify the use of the latter in designing control strategies. So actually trying to do sort of control, and in this case it's going to be using some sort of optimal control approach. It's very hard with a simulation. So you do the simulation, you match that to the analytic model. That gives you a sense that the analytic model is then useful. And then we'll use the analytic non-spatial model to find controls. And so this is just, there was data collected by Heather Davis, Kaz Taylor, J.D. Seville, and Don Strong. And this is the clone, was for the petri dish before the things grew together, we call it clone. A meadow would be the obvious thing. And this is the seed set of how many seeds there are per basically area. And in the same, this is different locations. In the same location, individual plants set far fewer seeds than they do if they're clones because it's wind pollinated, and if they're together, and also the pollen has to come from a different plant. They're not, can't pollinate themselves. So we can do a spatially explicit model. We can, we actually parameterize it both from data. It's very easy, as you saw. You don't have to do anything clever here because the only thing that's there is either Spartina or mudflats. You don't have to do anything clever in terms of analyzing using spectral approaches, etc. Just regular aerial photographs. And we match this up. We then try and see, do we have an analytic non-spatial model that will match this? And so the seedlings are produced from clones. Seedlings come from clones, or seedlings come from meadows. And as I said, we're going to use the area occupied, and that's again easy to measure. That's what we're looking at. And the rate at which seedlings are produced by meadows is going to be higher than that produced by clones. Then we scale things so that the clones next year come from the seedlings, and then there's some rate at which the clones grow, GC, and some probability, which essentially is eta is the probability they grow together to be put into the meadow class, and 1 minus eta then is the probability it stays a clone. And there's something, then eventually they become meadows, this term goes to here, and then the area occupied by meadows increases. You may be asking, there's one thing that we haven't put in, which is mortality, and they don't, under these conditions, at least over the time scales we're interested in, there is 0 mortality. So you can compare the analytical models, and give you the same effects. So in particular, it's important to include the Lee effect. The non-spatial analytic model is here. The spatial model is there. This is the area occupied basically out of a single kilometer. So in fact, there's some difference up here. It's not that important. And this suggests that we should be able to do our optimization on the simpler model. Control here in Willapa Bay, I don't have so many pictures of the control operation in San Francisco Bay, I'll get to later, is kind of difficult because you're working in salt water. There's a limit to, of course, what you can spray in water. A lot of it's mechanical. Then their control occurs. And for example, questions might be, how much mortality do you need to be removed every year to eradicate invasion within 10 years? And is it better to prioritize removal of the fast-growing but slow seed-producing clones, or is it better to prioritize the removal of the slow-growing but high seed-producing meadows? And we also might want to include preventing seeds being produced that could be carried to some area that has yet to be invaded. And so, very, very simple model. In the very first pass through, and this is work with Cass Taylor, who's now a former student, who's now a professor at Tulane University. And what we have here is the total amount of effort, which is expressed in the total area removed in a given year, and X is the fraction that's a removal of clones, and 1 minus X is the fraction of that effort to remove clones, and X is the fraction of that effort to remove meadows. And as I said, we want to minimize both the cost and the risk of colonizing other sites. And what I'm going to do is just give you results. The way we did this initially was to use a genetic algorithm approach, because this is still a complicated model to deal with at this point. We're going to make it simpler a little bit. And what you notice is that the optimal strategy here is basically remove all the clones first if your budget is low. If your budget is high, basically remove all the meadows first. And it turns out that if you really look carefully, if you really were to parse this, that essentially what the optimal strategy here turns out to be is to essentially put as much effort as possible into one class or the other until you've spent sort of as much as you can on that, and then start to do essentially the other one. And if you do the wrong strategy, here, again, look at the graphs below. Here we do get rid of things after a certain amount of time. If you do the wrong strategy and your budget is low, you begin to make progress, but then eventually you lose the invasion and things go off. And the high budget, you can still do it, but the cost is much greater. Now, this model, again, required a fair amount of computation to solve, as well as the fact that sort of why things were behaving the way they were was not 100% clear. So then what we did, or I did with Kaz and Richard Hall, is we said, look, if you want to control invasive species, you're probably going to be early on enough that you can ignore density-dependent effects. And you can actually capture some of the Lee effect, which I said was important, by having the growth rates of the different stages depend on the stage. You can actually sort of mimic the Lee effect. So we said, let's make this density independent. And just for purposes of illustration, we'll look at 3 classes of individuals, and I just changed the name slightly rather than seedlings, clones, and meadows, seedlings, juveniles, and adults area. If it's nonlinear, this would be dynamic programming, which is hard. As a matter of fact, if you make it all complicated, cursive dimensionality hits you, and the sort of number of different classes, for example, rather than being able to express the amount of area occupied by each of these is a continuous variable, you'd have to have a relatively small number of discrete variables. But we can simplify it because we're going to make everything linear. And this is it's just sort of a fun argument, is that without control, and it's linear, the number's 1 year ahead. This I'm calling a Leslie matrix, although it would be state structure. So you just would have a matrix that would tell you this is now a vector of the number of, say, seedlings, juveniles, and adults. And then, with control, 1 year ahead, you would get what you would have had without control, minus the effect of the control carried 1 year ahead. And then you could run this any number of years ahead. The number after t years would be what you would get without control, minus, and you would have to just go ahead the number of years that since you made the control in that year, the controlled part projected ahead. And this is where the great advantage of linearity comes. This was in a paper that was in theoretical population biology a few years ago. And you can ask what classes should be removed. Well, 1 year ahead, you should clearly remove the class that contributes the most area normalized by cost. That's easy. And if you look essentially extremely far ahead, the class that has the highest reproductive value, and this is this idea that was actually introduced to ecology by R.A. Fisher in his 1930 whatever it was book, which is really borrowed from economics, so it's kind of funny that you take the economic idea which went to ecology and now we're using it to answer an economic question. This is the same as essentially present value sorts of issues. It has to do with the left eigenvector corresponding to the dominant eigenvalue of that L matrix. But at the intermediate time scale, you should do a finite time horizon, but that problem was linear. And any constraint that I'm going to put on is going to be linear, so it's a linear programming problem. And those you can solve arbitrarily large ones. So, and as a matter of fact, Ben did a slight extension of this where we're looking at a sort of a big spatial thing with an economist who said, oh yes, but it's absolutely as easy to do as quadratic programming, so we did that just because you could, not because I think it really told us that much more. And so we did that, and then I'll later on, Richard and I did something having to do with removal and restoration. And basically, if you have a high enough annual budget, it's very easy, then this is the population size as a function of time. High enough annual budget, you can control the invasion. As the budget gets smaller and smaller, eventually you can no longer control the invasion of population sizes. And the other thing that becomes obvious is that the sooner you control things, the better off you are. And there's one more aspect. If you've ever, and you probably have at some point, looked at linear programming, maybe you haven't, but the solution is always at a vertex, which says that you should always go after one class first, and then once you've essentially spent as much as you can at any time on that class, then you might have some mixed strategy for a little bit. So, it's time dependent. The optimal strategy means that you really do change what you do during time. There's a huge cost of waiting, as you might guess, so you always go after everything first. And we get this nice bit if you have, should always go after one class. But what if it's just a bit more complicated? And so this is some work. Adam is a former postdoc who just started at Arizona State University. Ted Grosholz and Jim Sankurika are colleagues in my department. Ted's a field biologist. Jim is a bioeconomist, and Sonny was a grad student in agricultural and resource economics at Davis, who's now faculty job. We're back now in San Francisco Bay, and same idea. And here, actually, again, there's an eradication program run by something called the Invasive Spartina project. And the reason it's slightly more complicated, and I'm going to forget, they changed the name, it's just really nasty for the ornithological people to do this. We'll use the old name of California clapper rail. It's now like Wilson's rail or something like This is an endangered bird species. And the endangered bird species, since the native Spartina was eliminated in lots of places, has been using the invasive Spartina as habitat, so you cannot just go after it completely, but you have to save some. It's a very pretty picture of that bird. And this is the changing abundance, and so this is the red is the dots are locations, and the size of the dot tells you how much Spartina there was in terms of area, and it's the hybrid. This is to orient you in case you want. San Francisco's here. Berkeley would be about here. That's Treasure Island. Point Reyes, Orange County, and San Jose is down around here. And you see that much less area occupied 6 years later, and essentially you can't eradicate everything. So what we can do is we can take a model, and this is essentially like the one that Richard and I had started to look at, where we have invasive isolates or invasive seedlings, which turn into clones, and by isolates I mean seedlings or clones, which turn into invasive meadows. We can remove either invasive isolates or invasive meadows. We have this control, which turns into bare soil. We can restore things, and here we might want to do active restoration to provide native isolates, which would turn into native meadows. There is no arrow going here because you can't plant a meadow, you can only plant an isolate. So that's the other control, and essentially the bird depends on either this or this. That's why you see the bird there. And so one of the aspects is that the dynamics are such that in some sense, if you were just approaching this without the biology behind you, you would say, gee, let's just make some meadows. But there's a time scale problem. You can't just make meadows. They take time to show up. And this idea of waiting for the time scale of biological systems, of understanding the limits that the biology puts on the levers that you can pull in terms of control problems, is a really intriguing and important idea. And if I have time, I'll get to another. And so the optimal management is this is the invasive Spartina meadows removal, then you start doing replanting, and what you first do is you eradicate invasive Spartina until you're at the constraint for amount of habitat you have to leave for the clapper rail, at which point further removal is prohibited. You do that as fast as you possibly can. And then you do something which you would never do if you were just dealing with invasive species, is that you would plant native Spartina isolates in fully eradicated areas until they cover some fraction. And so you put these isolates in here, and then you also use the entire budget, and then you remove the remaining invasive Spartina, and then while the native Spartina grows, maintaining just enough total coverage, and then you spend your budget very, very slowly. And we get this all via the linear programming approach, get the answers out, it's all well parameterized. And one of the aspects is that you don't use the entire budget. And the other aspect would be too that we made the model stochastic to see that it's so robust to that. And we also satisfied the economists by doing it the way they would have done it, which is using optimal control on a continuous time model with nonlinearities. You basically get the same answers, but with a lot more effort, maybe not as much so direct understanding. So that's the end of one story in terms of that. And I'll spend 5 minutes or so going over the next story, which is how to deal with tipping points. And back to this picture, because I'm going to look at a specific system, which is corals. And this is work with Pete Mumby initially, and student of Pete's, and then finally Pete and Julie Blackwood, who was a former grad student who's now at Williams College, worked on this problem. And once again, this started with Pete doing a spatially explicit simulation model and us wanting to understand the dynamics. So we said, let's try a very simple non-spatial analytic models, see if we can get similar results. And the idea is that this is a healthy reef. This, as you can see, is an ugly reef. The macroalgae have grown over everything. Grazing is what prohibits macroalgae from taking over. And so we have a system where corals are overgrown by macroalgae, turf algae are overgrown by macroalgae, and turf can be settled by corals. If the corals die, for example, they can be replaced either by turf or macroalgae. We assume everything's happening locally. We're thinking about putting things together. And the only arrow that prevents everything from turning into macroalgae is the red one, which is caused by organisms which basically go along and eat the macroalgae. And in the Caribbean, where this was, the sea urchins died off. The only thing that was doing it is something called the stoplight parrotfish. And someone can look at the model that we develop. I'm not going to give you the equations right now. I'll give them to you in a little bit. And look at the bifurcation diagram. And grazing intensity is here. If there's enough grazing, the only outcome is a healthy coral reef. There's an intermediate region here with alternate attractors. Unstable is dashed, stable is solid. And we get a hysteresis, so if you move over here, you fall down, and it takes time. So the parrotfish themselves actually, unfortunately, are subject to fishing pressure, some of which is bycatch, some of which is, a little bit of which may be direct fishing. We can't make the grazing go up directly. The only thing we can do is to stop fishing on the parrotfish and then wait for their dynamics to take over. Parrotfish actually have a fairly short generation time, sort of on the order of a year. And what we can do is write down a very simple model where we have an overgrowth term. We only need, since we're looking at fraction of error, we assume there's nothing that's bare, so it's either macroalgae M or coral C, so we don't have to have an equation for the turf dynamics T, M plus C plus T equals 1. So there's an overgrowth term where the macroalgae overgrows the coral. There's a grazing term which says that there's a certain amount of grazing by parrotfish, and the parrotfish is just grazes each kind of algae in proportion to the fraction that that algae represents of the total algae there. So it's the total grazing rate times M over M plus T, and there's an overgrowth of turf by macroalgae, and remember T is 1 minus M minus C, and there's the grazing term, which depends on the population dynamics of the coral, but the coral population dynamics depends, the parrotfish population dynamics depends on the coral. They're territorial, they have all sorts of cool things, they change sex, they do all sorts of interesting behavior. And so the coral dynamics take that into account. And what we can do is you can sort of say numerically, look at the dynamics where you've got, you start with the macroalgae at their long-term equilibrium. You can ask and turn off fishing completely. If you're over here, the system's going to crash to the undesirable state. But if you're here, you can cross the line. If you suddenly change, turn off fishing, the grazing is going to jump up. You're going to be able to recover in time and not settle down to where the amount of change in grazing is going to work, and you're going to end up with a healthy. Now, the recovery timescale, however, depends on the fishing effort level and is not monotonic. And so on the left, there's a complete reduction of fishing, and the coral population is shown in the solid line. And you see that, surprisingly, after the first 5 years, things have gotten worse and not better. Interesting things is we now in California are at the 5-year stage of essentially after the implementation of a bunch of marine reserves and trying to evaluate what they've done. And one of the things they're supposed to do is help a fish that has a generation time of, say, 20 years and a maximum lifespan of 100. So you have to sort of at least do your analysis correctly. And what's kind of sort of disappointing is that on the right, and notice the time scale on the bottom, This is now 200 years and not 20. And then once again, the solid line is the coral. And after even 20 years here, things have gotten much worse, and then they recover. And that is a reasonable reduction in fishing. So once again, it's this interplay of thinking about control, and the constraints of the biological dynamics give you this interesting timescale problem showing up. And to put some realism on it is by the time we're out to here or here, it may be that ocean acidification is enough to wipe out the corals anyway, but we don't want to go there right now. And so to kind of remind you of kind of some of the themes is that if you're going to predict, you're going to need math, and if you're going to do management, any kind of ecological management, you have to do a prediction. Something which should be obvious, but a lot of people sort of tend not to think about it. And basically, you can't just say, okay, we're in deep trouble. We have to do things in a way that that tells us what's going on. We have to make the predictions on reasonable timescales. We have to readjust things. And I would argue that we need both mechanistic approaches and limits to predictions. And something which I haven't even attempted to do is to scale up to these sort of more global scales, which are going to be much, much more difficult than what I've talked about. So thanks very much for your attention, and I'd be happy to answer any questions. Yes.
Is it the same Spartina in Willapa Bay and in San Francisco Bay? Did I get that right?
So in Willapa Bay, it's Spartina alterniflora. In San Francisco Bay, it's a hybrid, presumably, between not only presumably, but much of it is, though it's not all genetically tested, between alterniflora and the foliosa. So in Willapa Bay, there is no native Spartina. In San Francisco Bay, there is a native Spartina. The native Spartina in San Francisco Bay either grows as high or as low relative to mean high tide, or whatever you want to call the level, as the alterniflora does, or the hybrid does.
Thank you.
So you gave us several great examples of how you can reduce the complexity of models based on the simulation, going from the spatial model to the analytically resolvable model, and also examples of how you can simplify the structure of the control.
Yes.
But I'm wondering, in the situation, for example, with multiple objectives, preserving the endangered birds and getting rid of the invasive plants.
Yes.
Is this really the result of rigorous multi-objective optimization?
Not really, because if you look at what I said you had to do, it really just says add a constraint, right? So what the bird does to you is to say there's a constraint. You have to maintain a certain amount of Spartina in the system. So it's not really multi-objective, but in some sense that's what in some sense all multi-objective really is sort of similar to adding a constraint in some sense.
I see, but the structure of the control which you developed, you presented it as a three-stage process. First you get rid of
so you run the
you can, then etc. That structure, was it recovered of the optimization where the structure was not?
No, that's right. So you just run it, you figure out the optimum, and it turns out that there is this, as I said, there is this organization which is funded through the California Coastal Conservancy, and I don't want to go through it. There's lots of interesting stuff to this project that I just touched on, that has been doing this, and they've been doing more or less exactly what we would suggest in terms of how you should approach the problem.
Can you say a bit more about the challenges
Of this problem? Okay.
Of convincing them that the strategy
Is correct?
is correct?
No, we didn't have to get, they're out there doing it no matter what. The question was that so we published this.
So they were already doing the right
They were already doing the right thing. So we didn't, well, the question is, how did they feel about us saying this at the same time that, telling them, okay, you're doing exactly the right thing. I don't want to go into a lot of its personalities, but some of the amusing things about this, maybe not, is that they do provide some overall direction, et cetera, but there are also something like 27, at least 27 different agencies involved that actually own the land on which things, or manage the land on which the things are taking place. So there's very interesting coordination problems. And of course, at least seeds will flow around the bay in ways that are not so easy for us to understand. It's very hard to do hydrodynamics in shallow water, and even San Francisco Bay is shallow water relatively. So there's very interesting sort of network aspects to this from both a biological standpoint and essentially a political science standpoint. So we've got some, we've been studying that in terms of sort of how information is propagated. So one of the people whose name didn't appear on the project is a political scientist who works very much on networks. So one of the reasons that our department, which has this odd name, environmental science and policy, you might think we'd be at each other's throats all the time, but instead we get along amazingly well, is because everybody's very quantitative. So we all have sort of the same view of the way you do science, whether it be social science or natural science. So there it's not. In terms of, say, the role of understanding the dynamics of the parrotfish and the grazing, that's another interesting one. And there, we've also tied that, we've got that piece of the model, but we've also done a model involving grouper, snapper, and parrotfish to try and understand some of the fisheries dynamics of this system and how you would manage this as a thinking about one species versus multiple. And what this work has done is it's shown the existence value of the parrotfish. It pays to keep parrotfish in the system. There's a large ecotourism industry, especially in the Bahamas, where we did a lot of this work. Fortunately, as it pointed out to me, I did this all wrong. I kept doing field work when I had a team, so I only got to the Bahamas once during the entire project. I was doing this all incorrectly. Other questions?
If there are no further questions, let's thank our speaker again, and we can ask additional questions. You can have them over the refreshments, which will be served in the main CAM student